All right, kiddies. Hey, well, it's good to see you back. And yes, for those of you wondering, I do have my coffee with me. Although you can tell, it's getting kind of cold. Don't like cold coffee. At any rate, my name is Mr. Krause. All of these videos can be found at www.nkinfinity.com. For those of you that are looking to buy this stuff, oh my goodness, Ms. Newman and I have tried to perfect this stuff and get it to a place because she and I are sort of, well, I would like to call us, what's the word I'm looking for? Perfectionist control freaks. Like, we don't want anything out there that's not perfect, and we know there's mistakes in this stuff, but it's getting good. It's getting good, and we should have it available soon. I apologize for those of you looking for it. We are going to have some review material available very soon. Keep checking back onto the website. And if you subscribed, and if you hit that bell next to the word subscribe, you'll get notifications of when we do some live streaming. And hopefully that'll help you out as well. Anyway, here we go. Today is day 2 of Unit 10, last unit. Oh my God, I keep thinking about that. Oh, it's so much fun. Anyway, day 2 of the last unit. This is a warm-up. Let me pause that right there. If you pause that right there, you should be able to go through and answer those questions based on what we talked about yesterday. So pause this face. Hey, you're back. I hope you paused it. Got a good screenshot. A parameter. I probably should have put a parameter. Parameter. A value associated with the population. Statistic. A value associated with the sample. What's the symbol used for parameter mean? Parameter mean, in other words, the population mean, that's mu. Parameter standard deviation, that's sigma. Sample mean is x bar. Sample standard deviation is just a simple s. Symbol used for population proportion. Now, population proportion is simply just a p, but a sample proportion is my p hat. That's what we're going to be using for sample proportion, p hat. And as we increase n, what happens to the standard deviation? We talked about this yesterday. The standard deviation decreases. Spelling deviation. That's embarrassing. Deviation. Decreases. All right, let's get started today. So yesterday we talked about this one underlying question. Do you agree the U.S. should not legalize the recreational sale of marijuana, as Canada just did? Unfortunately, it's not feasible to know what the population was. Remember yesterday I told you, we talked about it yesterday, we said, hey, let's say the population proportion is in fact 0.7. Well, where did we come up with that from? Would we just kind of make that up? I don't know where we came from with that. So here's how we're going to deal with this if we don't really know what it is. So we took a sample, and our sample said that 1,750 out of 2,500 people found that they agreed with the statement. Remember, this is a proportion. Proportions are not means. Proportions are yes and no. That's all there is to do with proportions. Yes and no. Yes, I agree. No, I don't. Yes, I'm a boy. No, I'm not. Yes, I have blonde hair. No, I don't have blonde hair. Okay? And it's the proportion of what are you looking for over the total. Okay? So in this case, we took a sample. And our sample was, we asked that question, and 1,750 people out of 2,500 said that they believe that we should not legalize abortion. In other words, they agreed that we shouldn't legalize it. So we came up with this 0.7, which is actually a statistic. It is a statistic. It is not the population proportion, mu. It is just an X bar. or excuse me, we're not working with means, we're working with proportions. So yesterday we talked about means a little bit with the fish, but then we really talked a lot about portions. So this is my p hat. This is my p hat. This is my statistic, or excuse me, my sample proportion. Okay, it is a statistic, but it's my sample proportion. And what we're trying to do is to use p hat in order to make a prediction about p. All right, so you can think about p hat is like the x bar of means, and p is the mu of means. But we're not working with means, we're working with proportions. So we're talking about p hat and p. Based on this sample, we can say, based on our sample, 70% of those sampled believe the United States should not legalize the recreational sale of marijuana. Of course, we need to ask this question. Is the statistic p hat a good estimator of p? And that really is it. And what we're saying here is, does our estimate of 0.7 give us a good estimate of what the actual 200 million people that can vote believe? Do we believe that 0.7 or 70% of the population believe this or not? Is it a good indicator? Now, I'm not saying, do you agree with it? I don't care if you agree with it. I don't care what your views are. I'm just basing it on this particular sample. And is this a good indicator of whatever? And that's the big thing some people need to realize is it's not based on what you and 40 of your friends think. Okay? Because what you and your 40 of your friends think, you might have a like mind. You have hell yeah, we should definitely. But maybe the overall population is different. So again, you got to take yourself out of this. And is it a good estimator of the population? Remember, parameter is a population. So we're looking for the population parameter p as opposed to the statistic. Is it a good indicator? So the example we walked through yesterday started with a sample of n equal to 100. All right, and when we had n equal to 100, we got a pretty good normal distribution curve. However, when we used n equal to 2,500 in our sampling distributions, we were able to see what? What were we able to determine yesterday by increasing from 100 up to 2,500? Well, either way, we were able to see that the sampling distribution was, sampling distribution of the sample proportion, P, of the sample proportion, P hat, is approximately normally distributed. You always have to say approximate unless it's perfect. And it's probably never going to be perfect. So it's approximately normally distributed. I forgot to take a break. Let me take a break before I start this one, because I want to check the audio. Okay, forgot what I was going to say. Okay, so what's our second thing we said? Okay, so the mean of the distribution is close to the population proportion P. And actually, in reality, the mean of all population proportions is going to be equal to P, and it will be exact. So if you take all of the means of all the populations, it will be exactly equal to the p. And the big thing I think we want to talk about is the fact that the standard deviation decreases as we increase the value of n. So as n increased, it decreased. Now, you remember those pictures from yesterday where I showed you a normal distribution and I increased it from n equals 1 to 100, and they all went to 2 columns. Same distribution, same horizontal axes, but they all went to 2 columns. And then when I looked at those 2 columns and I said, okay, we're going to blow those 2 columns up, and I spread them all out into different intervals, then I'm like, oh, wait a second now. It's normal distribution, but my standard deviation went down by a ton. So, sample distributions of a sample proportion. We're going to talk about the procedure now. We're going to formalize it into a procedure so you can talk about how you're going to do this. Okay, so how is this going to happen? Oh, I was thinking I put a formula on the other page, and I keep going back to it because I think I messed things up. So if we're interested in discovering information about the population proportion P, which we'll never know the actual value. It's just impossible. We must choose a simple random sample, and we talked about simple random samples many times, of size n, which is sufficiently large enough in the population. Size of the population, and this restriction is outside the scope. I forgot what I was going to do. When you get into AP statistics, they're going to make you test to make sure that it's appropriate. In our class, you're going to assume it is appropriate. In general, the size of your population has to be at least 10 times the size of your sample. So like if I was going to sample Hilton High School, we have about 1,500 students. I couldn't sample more than 150 kids because that's 10%. So I'd have to, that's 1/10 of the population. So I want to sample less than 150 kids. But I would only have to sample maybe 30 or 40, depending on how the original shape of the original distribution is. But that's outside the scope of this. So based in a simple random sample size n, we'll assign the proportion sample to p hat, which will have the following characteristics. Okay, what is p hat going to have? The sample distribution of p hat. So what's this thing going to look like? Is approximately normal and becomes more normal as the sample size n increases. As the sample size n increases. And we've already talked about that. It gets a better normal shape. Not only does it get a lower standard deviation, it becomes more normal the higher you pick n. The mean and sampling distribution is exactly, so the mean of the sampling distribution is exactly equal to the population parameter P, equal to the population parameter P. The standard deviation of the sampling distribution, and this is the kicker. The standard, this is where we're going to start doing some math. The standard deviation of the sampling distribution is. And here's a formula we're going to learn. So the standard deviation of the proportion of the sample proportion, the sampling distribution, is equal to the square root of p times 1 minus p all over n. So let's talk a little bit of number theory. Hold on, do I have time? No, hold on, I'll be right back. All right, so let's talk about a little bit of number theory. If I take 10 and divide it by 2, I get 5. If I take 10 and divide it by 5, I get 2. If I take 10 and divide it by 10, I get 1. So as my denominator increases, what's happening to these numbers? They're getting smaller. Now that should make sense. As you divide by a larger number, the fraction gets smaller. Well, think about it. Does that make sense with what we've talked about already? As n gets larger, doesn't this fraction get smaller? And if you take the square root of that small thing, it's small. So as n gets larger, my standard deviation is going to get smaller. And a little bit of math fun. What would it take to have the standard deviation? So for example, if you want to have something, let's say I take my standard deviation is 4. So I'm going to divide by 5 and I get 4. So what if I want to have that standard deviation? So I want my standard deviation to now be 2. So what would I have to do? 20 divided by 10, right? I would have to double this in order for this fraction to have. Now let's talk about with square roots. What would I have to do with square roots? Let's say I start, I don't know if 20 is such a good example. I'm trying to think of a good number. It doesn't matter what the numerator is, but I want my standard deviation to go in half. So I want this to go from 10 to 5. Well, what am I going to have to divide by? What n value? What am I going to have to do to n in order to get my standard deviation to go down to half? Well, I want to cut it in half, which means what do I have to do to this n value? Does anybody know? You have to increase it by a factor of 4. Of 4. Now, why 4? Well, what is the square root of 4? Oh, it's 2. So really, if I take this thing and I increase it by a factor of 4, I do 4 times it, I'm really dividing by the square root of 4, which is really dividing by 4 times, dividing by a number that's 4 times larger. And if you take the square root of that, it's really only 2 times larger. And so if you're dividing by a number that's twice as big, going back to this example, you cut your standard deviation in half. A little bit of math fun. Let's see what we got. So we're going to draw I didn't draw this in my notes. I don't know why. So I got my sampling distribution where p equals 0.8 and standard deviation of 0.4. So this is 0.8. And I had a standard deviation of 0.4. Right? So this would go 1.2, 1.6, and 2. 0.4, maybe this is a bad example, 0, and then I really wouldn't go any further. That's probably a bad example. Maybe I should change this to, I'm going to change this in my notes to 2. Instead of my p being 2, I'm going to make it 2. So let's say my p value is 2. So I go by 2.4, 2.8, 3.2, and I go 1.6, 1.2, and 0.8. Okay, so I have a p-value of 2. Now, what would this standard deviation look like if my standard deviation went down to a 0.2? Down to 0.2. Well, instead of my first standard deviation out here, my first standard deviation would be out here, and here it would be at 2.2 and 1.8. And then my second standard deviation would be here. And so this is still my mean. And my third standard deviation would be right here. So remember that diagram we did a long time ago? It would be a really skinny normal standard deviation where the spread is not as spread out. That's terrible to see. I'm going to do it with this big fat black pen. So it's not as spread out. So by doing that, by increasing this, or by decreasing the standard deviation, and to decrease the standard deviation half, n has to get multiplied by a factor of 4. I've taken a standard deviation that was this wide. By increasing my n value by a factor of 4, I've cut it down in half. Well, that means I've got a better accuracy. I can make better prediction on what's going on. All right. We'll use this information later to talk about confidence intervals. Confidence intervals are what we're going to be talking about a lot this unit. Intervals. Well, we're going to be talking about it a bunch. But we'll use it. Oops, I didn't mean to cross that off. I meant to underline it. We'll be using that. We'll be talking about that a lot, or quite a bit, about how confident are we about your data. Because think about it. If I've got a certain standard, if I've got a certain population thing that I'm trying to estimate, what n value do I have to use? In other words, when I say what n value, how much money do I have to spend? How much time do I have to spend in order to get relatively accurate information? It's kind of one of the things we're going to be talking about. All right, it's time to do math. I know you guys are talking about all of this theoretical stuff. It is time to do some math. So, as you know, Ms. Newman and Mr. Krause are into fitness and healthy lifestyles. So last month, they decided to find out if students are exercising on a regular basis. They asked a simple random sample of 800 high school students in Monroe County. Clearly, the population of high school students in Monroe County is much larger than 8,000. And I only include that because later on, when you get into higher level statistics, your sample has to be less than 1/10, or your population has to be at least 10 times the size of your sample. We know from the census that all high school students are mandated by education department mandated by the state education department so we know from a census. I'm sorry, I forgot what I was going with this. We know from a census that all high school students of all high school students, because it's mandated by Monroe County, that 28% of all students exercise on a regular basis. So what am I telling you? I'm telling you P. I am giving you P. I'm giving you a P-value of 0.28. That's the population parameter. Population parameter for this particular problem, or population proportion in this case, the parameter proportion if you want. So let's see what we know. Let's write down what we know. We know that we have an n value equal to 800. We know that we have a p value equal to 0.28. So we need to figure out what our standard deviation is. Now, what we're also going to assume that since because of our p equal at, and I said if we have a sufficiently large enough n value, we can assume our p hat is equal to our p, which is equal to 0.28. All right, so we know all this information. We need to calculate the standard deviation. So that's our first calculation. I gave you the formula on the previous page, standard deviation. And that is the sigma of p hat is equal to the square root of 1 minus p over n. What am I doing? That's not it. It's P times 1 minus P. In other words, it's P times P complement is what we got here. That's really what we got there. P times P complement. So P is 0.28. The complement of that would be 0.72. And we're going to divide by 800. So we're going to get some standard deviation. I got to grab my calculator for that. Make sure my calculations are correct. Ding. Oops, excuse me. So square root, control division of 0.28 times 0.72 all over 800. And we get a standard deviation of 0.0159. So 0.0159. 4 decimals should be enough on this one. Now what are we going to do with that? We're asked to find, what is the probability that a simple random sample will give a result within 3 percentage points from the true value of 28%? Wait a second. What I want to figure out is, we're doing a sample. The true value is 0.28 or 28%. We want to figure out is, if we do a sample, what is going to be the probability that I'm within 3 standard deviations of that? Okay, 3 percentage points. In other words, I want to know the probability. We need to find. I'm going to do this in a different color because maybe I'll do my math in red. We need to find the probability that P hat, falls between 0.25 and 0.31. Now, where the heck did I get those numbers from? Yeah, that's plus or minus 3%. So we need to recall. Now we need to recall from chapter 8. That's why we probably should have done this right afterwards, but that's all right. It's a good review of chapter 8. We need to come up with some z-scores because we're going to have to use our, where is it? There it is, our our z-score table. So we're going to do 2 examples with this. So first things first, we're going to create our z-score. In this case, our z-score is going to be 0.25 minus 0.28 divided by our standard deviation, which was 0.0159. All right, so I'll go with my calculator. Control division. 0.25 minus 0.28 all over 0.0159. Z-score of negative 1.89. So this gives me a z-score of negative 1.89. Now I got to create my other z-score. I should be doing this in red, right? 0.31 minus 0.28 all over 0.0159. And it should come as no surprise that this is going to be 1.89, right? Because if that's 0.3 up, that's 0.3 down, it's going to go the same standard deviations. So now let's draw our normal distribution curve. Oh yeah, you thought you're going to get away from this. Normal distribution curve. We got our negative 1.89 here. Got our positive 1.89 here. And we want all of this in the middle. Because remember, we think our p hat is somewhere between these 2 places. All right? So we got to figure out what that is as a percentage. So remember, looking up scores only gives you the information in the tail. So we're going to have to remember to do a little bit of math. So let's go find 1.89. 1.89 is right here. 0.0294. So let's go back. So this is 0.0294, and this is 0.0294, correct? So, how am I going to figure out what's in here? Oh yeah, we got to do 1 minus 0.0294 minus 0.0294. And let me grab my calculator. 1 minus 0.0294 minus 0.0294. Yes, I could have done 2 times that. Equals 0.9412. So, what do we know? What does this tell us? So we know then, so based on a sample n equal to 800, we know that 94.12% of all samples of this size will yield results p hats within 3 percentage. I was going to put plus or minus, but I said within, with percentage points of the known population. And then later on, we're going to figure out what happens when we don't know P. Now, let me make sure you understand what happened here. So, I do a sample size of 800 students. I gather information about 800 Monroe County students. And student X does 800 students, and student Y does 800 students, and student P does this person, and Mary, and Jane. And we all did. If I had 20 people that did that, 94% of them would have standard deviations that fall within 3 percentage points of the actual mean. In other words, whatever mean they came up with would be somewhere between 0.25 and 0.31. Now, one person, now I say one because I said 94, so that's almost 95. So about one person would have a number that was outside that. They might gotten 32% or 33% or 24%. But the rest of us, 94% of us, would be within 3 standard deviations. That's how confident we would be. All right, we're going to keep going. I should have made one last point clear, and I want to be very, very clear with this. This 3% plus 3% and minus 3% that we put right here, this thing right here, had nothing to do with, if you go up 3%, down 3%, that's 6%, and that's why we came up with 94. That was just dumb luck. That doesn't happen very often. Okay, we did all that math to come up with 94%. Don't think you're going to be able to, if I said 8%, you're like, oh, go up, down 8%, up, down 8%. Oh, that's 16%, so we're going to have a 94%. An 84% chance because down, that's 16%. No. That was just dumb luck, okay? So let's talk about example 2 for today. As you know, statistics are easily manipulated in order to sway different groups of people into believing one thing or another. Easily. And the more you study statistics, the more you can fool 99% of the population into anything you want them to believe, because not enough people understand statistics. They just go by feelings. They go by like, ooh, big numbers must be right. Or person said it really smartly, so it must be right. And I know smartly is not a word. Intelligently, so it must be right. Many times, sample surveys have what's called undercoverage bias. They're missing an entire group of people. Most of the time, this is due to inappropriate sampling techniques, but sometimes it's clearly done in order to fool the reader. A simple way to check for undercoverage bias is to compare the sample data to a known fact about the population. So there are tests of your tests. So as you get better at statistics, you'll start doing tests of your sampling technique to see if you have bias. And if you have bias, bam, you got to throw out all the crap and start over because you screwed up. Okay, so that's why you want to make sure that when you do a simple random sample, it is indeed random and you don't have one bias or another. So we're going to talk about undercoverage bias. I am not trying to get too political, but this is a very hot political problem, and I want you to understand how I can manipulate you, or you can be manipulated into thinking one thing, but maybe that's not quite true. Now, again, some people, no matter how many times you throw the facts at them, they will still go on what feels good as opposed to what is actually good. Now, this stuff is made up. All of this stuff in this problem is made up. It has nothing to do with anything other than to be made up and for you to see what's going on. So, in order to determine how people really feel about President Trump's goal of building a wall along the U.S.-Mexican border, a group of college students decided to conduct a survey. That's a hot topic right now, so why not address it here right head on, math class? I don't care how you feel about this one way or another. I have my own opinion. You have your own opinion. Don't care. This is math. We're going to crunch numbers and see what's going on. That's all I want to talk about. So, we know that the U.S. population has approximately 17% Hispanics. That is a fact. I didn't make that up. Approximately 17% of the U.S. population is Hispanics. The proportion p-hats of Hispanics in a simple random sample of 2,200 adults should be approximately 17%. So, if I conduct my survey correctly, then my sample of 2,200 students, of 2,200 people, should have approximately 17% Hispanics. If I don't have approximately 17% Hispanics, does that mean I am cheating? I don't know. Sometimes when you conduct an experiment, you're going to be off. How far off is acceptable to you? How far off is 15? So in this case, in a survey, the college students determined that 15.2% of the respondents were Hispanic. Are you okay with that? Is that acceptable to have 15.2% of the respondents Hispanics? That's really, really close to 17. It's not even 2% off. It's not even 2% off. So yeah, that's pretty good, right? That feels good. 15.2% is close to 17. That feels good. I think that's okay. That is unacceptable in the math world. That's not acceptable in the math world. And when you want to do statistics, you have to do it correctly. So is it acceptable? I don't know until I run the numbers. And that's what we're going to do right now. We're going to run the numbers. And we're going to see if the Hispanics were underrepresented. Because clearly they weren't overrepresented, because 15.2% is less than 17%. So here's what I want to find. If this was done correctly, then most of the time, like in this last problem, most of my p-hats, 94% of all the samples of everybody that did it would fall within those 3 percentage points. So what I want to know is, will the vast majority of samples of size 2,200, will it have, will 15.2% fall in that area? I don't know. So let's see how this works. So here's what we know. Have I talked long enough? I'll be back. I'm going to come back and do the math. So our goal is to figure out, did this happen? Did this 15.2% happen by mere chance, or sheer chance, mere chance, sheer chance, by chance. How about by chance? By chance or on purpose. We're going to find out. All right, let's check this out. What we know that P is equal to 0.17. That was given. That is a U.S. Census statistic. That is indisputable. You cannot dispute that there are 17% Hispanics because it is a known population parameter. It is known. So you're Hispanic or not Hispanic. Parameter, right? So let's see what else we know. We know that our n size was equal to 2,200. What do we have to find? We need to find our standard deviation. So we're gonna make our p hat equal to 0.17. Again, later on we're going to find out what happens when we don't know this, but that's later. So let's find our standard deviation. Our standard deviation of p hat is going to be equal to, we talked about this, p times 1 minus p over n. Write it a few times. So 0.17 times 0.83 over 2,200. So we'll go over to our calculator. Not this. We'll go over to our calculator. Why do I keep doing that? Okay. So square root of division. And then we're going to do 0.17 times 0.83 divided by 2,200. Wow, look how small that is. Now, why is that so small? It's 0.008. That's our standard deviation. Look how small that is. Well, you tell me why it's small. How did I know that was going to be small? Should I have known that was going to be small before I even grabbed my calculator? Oh yeah, I should have known that was going to be small before I even grabbed my calculator. And you know what? Let's make it a little bit more exact, 01. Okay, so 0.00801. So here's what we need to do. We need to come up with a z-score. So we're going to do z. So z is equal to 15.2, that's our observed value, minus 17 over our standard deviation, which is 0.00801. And we're going to get a z-score. So let's go to our calculator. 15.2. Excuse me. Got to work all in the same percentages, kids. 0.152 minus 0.17, right? Isn't that what I used over here? 0.17. I got to use the same stuff. So where's my backspace? Come on. I got too many papers in my way. Let's do control division first. Let's do this the right way. Control division. So 0.159 minus 0.17 all over 0.00801. That's... Did I miss a value? Oh, it's not 159, it's 152. That's why. My number was not... Oh, wait, jeez. Enter. It's 0.152. Because my number was a lot different than this. All right, enter. It's going to be a lot different. All right, there it is. Negative 0.225. So negative 2.25, right? Negative 2.25. And we knew it was going to be negative because it fell to the left. So let's take a look. Grab our standard deviation curve. And negative 2.25 is down here somewhere. Remember, this is 0 right here. So we want to know what percentile this lies in. In other words, we want to figure out what all of this is. What is this percent that's lower than this? In what percentile does this lie? So we're going to go to our Z table. We're going to go look at our Z table, or our, Z table on the next page, negative 2.25. I think it's this one right here. 0.0122. So, it's in the same, lose my mind. 0.0122. I forgot it was on the same sheet. So this area is 0.0122. Now, what does that mean? What does that mean? Well, let's think about that means. What this tells us is in all sample sizes where n equals 2200. Now, the reason my standard deviation was so incredibly tiny was because I had a ginormous sample. 2200 is a huge sample, right? That would make up for the fact that you missed a lot of Hispanics, because if you're going to check all over the place, you're going to find a place maybe where you got a lot more Hispanics, because you got a lot of people, so that should cover that. Okay, so let's see what's going on. In all sample sizes where n equals 2,200, we know that only 1.22% of these samples would have so few Hispanics. So let's see if that makes sense to you. In other words, let me just talk. In other words, I'll write it down so you have it. In other words, if we conducted, I wish I could write faster than I can type. If we conducted this survey 1,000 times, if we conducted this survey 1,000 times, in those 1,000 surveys, and I apologize if that's behind my head, in those 1,000 surveys, only 12 of them would have a p-hat less than or equal to 15.2%. Or in other words, only 12 of them would have a population of Hispanics so low. So, can this happen by chance? Well, if it only happens 1.2% of the time, would you say that's by chance or by design? I would say that's by design. So therefore, the random sample suffers from under coverage bias. The Hispanic population was vastly underrepresented. So somehow the way they collected the data was faulty. Now let's be honest with you. Be honest with yourself. We said originally, if we take back a look at the original problem, and I'm with you on this one because I'm as guilty as the next person, not anymore in my life because I'm a little bit more discerning. I saw these numbers of 17% Hispanics, and in our population, 15% Hispanics. And I said, oh, okay, it's about right. And I thought that was no big deal. But since that can only happen 1.2%, 22% of the time, the way the data was collected was faulty. We have undercoverage bias. And as soon as you have bias, this survey, no matter how much you feel it's good or how much you feel it's bad, is not a good study. Now, the reason it's so low and the reason it's such a small sample is because our N value was so ginormous, right? What would happen if we decreased that N value? Let's say we took that N value and we made N equal to only 500. Oh, not 5,000. Let's say we took N equal to 5,000. So then we would have a standard deviation of 0.17 times 0.83 divided by 500. Let's see what that standard deviation is, and let's see what that does for us. So now we have a standard deviation of 0.168. Well, we'll do 0.160. 0.01679. And then we'll take this. We'll do the same math. Oops. We'll divide by 0.01678, whatever. And we get a z-score of negative 1.07. So now our z-score is negative 1.07. So now I'm going to look that up. 1.07. 1.07. Let's see, this is 987. There it is, 1.07, 14.23. So what would that tell us? Oh, shoot. 14.23. So if we had this one, right, then if this was it, then 14.3% of size of N equal to 500 would give us Hispanic populations of 15.2%. So if we were to survey only 500 people, we would come up with 14.3% of the surveys would have such a low number of Hispanics, a Hispanic population of 15.2%. So, in other words, is that by chance? Is that good enough for you? I still think that's quite low. 14%, only 14%. So if you conducted a survey 100 times and 100 people went out and collected 500 a survey and surveyed 500 different people, and you took those 100 surveys, of those 100 surveys, only 14 of them would have such a low Hispanic population. So even that would be still low. But notice how drastically different. It's 14 times larger. It was only 12% or 1.2%. Now it's 14%. So just by increasing the N means we're going to decrease the standard deviation, which means we become more accurate. We should be more accurate. So by having an N size of 2,000, that means this value right here, this 5.2, probably 15.2, should have probably been somewhere around 16.6 or 16.8. Even that would probably be low. But by this maybe being 16.8%, then we can say, okay, the survey was pretty good. But being at 15.2, never, not going to happen. So what am I trying to get out of today's lesson? I want you to understand this. That just because things look good, just because someone is on TV telling you these numbers, you can't always believe what numbers they do. Lots of times people do convenience surveys. They just go out and do whoever's around. That's going to be undercoverage bias. Most of the time things are done, it's painful. And it's really important that random samples are done accurately. And that takes work. It takes good design and it takes good work. And people that don't go out and do good design and don't go out and do good surveys and sample might give you faulty numbers. But you might believe it because you're thinking, oh, look, it's only 1.8% difference. That's nothing. That's nothing. Okay, one person, big deal. Who cares? It is a big deal. It is a big deal. So hopefully you're becoming a more discerning statistician or follower of numbers and not so blinded by the vagueness of numbers and getting the wool pulled over your eyes. That's the end of day 2. Hit the subscribe button, hit the like button. Hopefully this kind of stuff's kind of cool. I like it, and I hope it makes sense. I think eventually it will. You're going to have a couple of these kind of problems. Follow the procedure that I showed you here, and you'll be okay. All right, kids. Catch you on the flip side.